For this lesson, we're going to be taking a look at applications of quadratics in factored form. So we've already looked at quadratics in factored form quite a bit. We've looked at the skills required to switch from standard form to factored form, and we've looked at the idea of zeros from factored form and what you can get from that. We're going to be extending that here today. So let's take a look, jump right in, take a look at our first example here. So we've got a rectangular lot bounded on one side by a river and in the other three sides by 80 meters of fencing. It's never a bad idea to start with a diagram, however poor your artistic skills might be, as I'm about to demonstrate. So I have my poor excuse for a river here, and then on the other three sides, so here is the lot, and it is bounded on one side by the river, the other three sides by a fence. So my fence, typically when we think of, we've got a rectangle here. So normally we talk about a length and a width, and because it's a rectangle, this of course is going to be length as well. And we know we have this relationship, which is that the other three sides are enclosed by 80 meters of fencing. So that means I can actually say that this length plus this length, which is two lengths plus a width, is equal to 80. So there's a relationship between length and width. It's not quadratic though. And there's a reason why it's not quadratic, is because we haven't actually addressed all possible relationships here. There's another relationship that we're going to be interested in, and it's this, which is, what is the question actually asking for? It wants the dimensions, meaning length and width. So that's what we're trying to find. Our goal is to find length and width of the largest possible lot. But when we talk about how big a lot is, that is talking about the area of a lot. And so the area of this lot is length times width. Now if we take a look at these, neither of these is actually a quadratic, at least not in terms that we've talked about before. But it turns out that with a little bit of thinking about it, this length times width actually is quadratic, because this is an order 1 term and this is an order 1 term, and so if you add the orders of these together, that's order 2. So this is actually quadratic. But what we'd like is to put this into a form. Let's just undo that. What we'd like to do is to put this into a form that is a quadratic of only one variable, which is all we've learned to work with so far. So the way that we do that is we replace one of these variables. Since this one is already isolated for w, sorry, not isolated, but w has a coefficient of 1, I'm going to isolate it for w, and that becomes 80 minus 2L. And now if let's call this equation 1, I'm going to sub 1 in 2. So this is equation 2, and so equation 2 becomes length, but instead of width, it's going to become 80 minus 2L. And now we have it's still a quadratic equation. This is order 1, this is order 1, so the overall is order 2, but this is now a quadratic equation in one variable, which is what we want. It's what we're familiar with. So that's one of the things that you want to work with. And just to remind you, this looks like something we've had before. In the past, maybe we've had y equals x minus s x minus t. So we have our independent variables on the right, that's the L, that used to be the x. We have our dependent variables on the left, that's the A, in this case used to be the y. So I don't want you to get too disturbed when you see these things if they don't quite match the variable expectations you have. The other thing that some people have a hard time with, or at least they overlook it, is this idea of the L. Why is there not something subtracted or added? Well, the thing that's being subtracted or added here is a 0. The point is, this is factored form because we have a factor multiplied by another factor. Now we are trying to find the largest lot possible. And so what does that mean? Well, largest, another word that goes with largest is maximum. And when we talk about the largest lot, we're talking about the maximum area. So we are trying to find the maximum area of this lot. Well, here's an expression for area. How do we find the maximum? Now, something to keep in mind is that this is quadratic. If it's quadratic, it means it could be a parabola opening up or a parabola opening down. For it to have a maximum, it's going to have to be this one. And where is that maximum going to occur? It's going to occur right here. And that point where it occurs is called the vertex. So we are interested in the vertex of this. So let's take some of these away. And so what I'm going to say from here in red is that we want the vertex. And how do we find the vertex from factored form? So from factored form, so let's actually put in here from factored form. So how do we get the vertex from factored form? The first thing we need to do is we find the zeros, and this is something we've done in a previous lesson. Once we find the zeros, the next thing we do is we find the midpoint of the zeros. And what does the midpoint of the zeros give us? That gives us the axis of symmetry, but the axis of symmetry is also the x-coordinate of the vertex. And then once we have the x-coordinate of the vertex, we can then sub the x-coordinate of the vertex, and we can find the y-coordinate of the vertex. And now we would have the full vertex. Now, it turns out we're not going to need this step 3. We're actually going to have a step 4 that's more useful to us. But let us proceed as if we're doing these, because we are going to do 1 and 2. So let's just move over here. I'll do them beside. In order to find the zeros, in the past what we've done is we set y equal to 0. But I don't have a y in this case. What is my dependent variable? It's the letter a. So what I'm actually going to do is I'm going to set a equal to 0. And so when I do that, I get 0 equals L times 80 minus 2L. I've got something times something. So this thing times this thing equals 0. The only way for that to happen is if L is equal to 0 or if 80 minus 2L is equal to 0. But this one's easy enough. L is equal to 0. Here, I end up with 80 equals 2L. Divide both sides by 2. I end up with L equals 40. So those are my two zeros. I'm going to find the midpoint of the zeros. And the reason I want to do that is to find my x-coordinate of my vertex. But I'm not finding the x-coordinate of the vertex. I'm actually finding the L-coordinate of the vertex because my variable's changed. So make sure you do that one. Make sure you recognize that change in variable. And then I just take the two zeros, add them together, divide by 2. 40 divided by 2 is equal to 20. So that is the length that gives the maximum area. So this is the length for the maximum area. And the reason why I said, so we've done 1 and we've done 2. The reason why I said we won't need 3 is because if we go back and take a look at our original question, we are interested in the dimensions of the largest lot possible. So we're interested in L and we're interested in W. Well, now that I have the L that I need, can I find that W? I can actually find that from here. W in terms of L. So I can just sub that L in. Nowhere in this question did it actually ask me for how big is that actual lot. And that's the piece of information that I would get from here. This would tell me how big the lot is. So what is the max area? But we're not interested in the max area. So since we're not interested in the max area, we're not interested in this step. Instead, we're going to add one extra step here, which is we're going to sub the vertex value for the length to find the vertex value for the width. I don't like that because the width, we could have done this in terms of the width. So let me instead just say we're going to find W. And so that's now what I'm calling step 4, having skipped over step 3. The width is equal to 80 minus 2 times the length. I make my substitution. The width is equal to 80 minus 2 times 20. The width is equal to 80 minus 40 is equal to 40. Therefore, dimensions are 20 meters by 40 meters. And if you've got a diagram, you've made it clear enough that this is a length and this one is the width. But you might want to, if you are just writing this in text, you might want to say 40 meters parallel to the river, just to make it really clear that the 40-meter side is this long side, which is parallel to the river. That's not a bad idea to include that. Okay, so there's our first application question of a quadratic. All right, next one. Supermart cashiers try to memorize sale prices while they work. A study showed that on average, the percent of prices memorized after T hours is given by this form. What is the greatest percent of prices memorized, and how long does it take to memorize them? So again, the greatest percent, we are trying to find the maximum of P, and how long does it take? So here we're trying to find out what T gives the maximum. That's what that one's. So this is asking us what is the maximum. This one is asking us what T value gives the maximum, and that T value that gives the maximum is the T value of the vertex. This value is the P value of the vertex. So now we actually have to find both coordinates of the vertex. This is our dependent variable. The P is our dependent, so just don't forget that's the same as our Y, and this one is the same as an X. And this is the same, actually, well, this would be an X squared. Okay, so that means that this is going to be in the X coordinate location. Our vertex, where we would have an X, we're going to have a T instead, and where we would have a Y, we're going to have a P instead. Okay, so now let's actually do the mechanical work to get us there. We have an equation here, but this equation is in standard form. There's no constant on the end here. That just means there's the constant of 0. But we want factored form. So let's just copy down the equation here. P equals negative 40 t squared plus 120 t. We want factored form, and as I've tried to stress, the first step in factored form, the first step in any factoring is common factors. So here I've got a negative 40, here I've got 120. So negative 40 is common. Usually you keep the sign of the t squared. You want to take that out. And I've got a t squared and a t, so I'm going to take out a t. What's left behind? Negative 40 divided by negative 40 is positive 1. T squared divided by t is just a t. Positive 120 divided by negative 40 is equal to negative 3. Be careful with that one. And then t divided by t is just 1. So that is my equation now in factored form. So that's, let's say that was my first step, which was to factor. And that's complete. My second step is to find my zeros. And to do that, I will set P equal to 0. So I get 0 equals negative 40 t times t minus 3. Now ask yourself, what are the things that are being multiplied together here? I've got the number negative 40 multiplied by the factor t multiplied by the factor t minus 3. Negative 40 can't be 0. It's impossible. So there's no point in even considering that, but I've got t times t minus 3. So that means that t equals 0 or t minus 3 equals 0. And when I solve this one, I end up with t equals positive 3. It's another example. This is a real life problem. What t, which is time, can time be 0? Yeah, that makes sense. Can the person have spent 0 hours trying to memorize prices? Yes. Not a very good employee, but it is possible. Can a person have taken 3 hours to memorize prices? Yes. So you want to do a little check there just to make sure your numbers make sense. And now, that's 1, that's 2. Let's go down here to 3. We want to find the t value of the vertex. So the t value of the vertex, which is the midpoint, or let's write it another way. That's the t value of the midpoint of the zeros. And the zeros were 0 and 3 divided by 2, which is equal to 3 over 2. Or, as a non-repeating decimal, it would be acceptable to write that as 1.5. You know my preference is to write it as 3 over 2, but 1.5 would be acceptable in this case. So now that we found the t value of the vertex, we know that you want to study for 1.5 hours to get the most out of this. And now we want to find what is my p value of the vertex, which is the max percent. And the way we do that is we sub it in. So the p value of the vertex, we're going to sub TV. So we go to this equation. We can go to our original equation or we can go to our factored form equation. It actually doesn't matter. Rather than squaring this fraction or this decimal, I think I'm going to work with the factored form of the equation. Negative 40, and instead of t, I'm going to put 3 over 2. And then I'm going to have t minus, oh sorry, not t minus, I want to replace that with 3 over 2 minus 3. Now in this case, I probably would have been better off writing this with the negative 1.5, or sorry, with positive 1.5. Just makes it a little clearer, especially on that subtraction. Negative 40 times 1.5, and 1.5 minus 3 is negative 1.5. And so that works out to be, I've got a negative and a positive and a negative, so the overall is going to end up being positive. And then I've got 40 times 1.5, and that is equal to 60. And then I've got 60 times 1.5, and that is equal to 90. So we end up with positive 90 as our answer. And then we go back and we take a look to make sure that we've answered everything. Well, we kind of made this very clear at the outset, and this isn't a bad idea to really make sure that you know what it is you're trying to find. I found what time gives maximum percentage, and I found that maximum percentage. So the time is 1.5 hours, and the maximum percentage is 90%. Therefore, maximum percent, actually let's write it this way, maximum of 90% after 1.5 hours. Next one. A ticket to a hockey arena costs $3. The arena holds 800 people. At this price, every ticket is sold. A survey indicates that for every dollar increase in price, attendance will fall by 100 people. What ticket price results in the greatest revenue, and what is the greatest revenue? Now this is a tough one, first time people are seeing this one, to set up the equation. So what we are interested in, first of all, is this idea of revenue. So let's just outline revenue. So what is your revenue? That's how much money you bring in. So you can see here, at the kind of the default setting here, this first sentence, if I look at the revenue implied in that first sentence, it's saying that I've got a $3 ticket being sold to 800 people, because it says at this price every ticket is sold. So this is a full house under the current conditions. Now, how will this change? If I increase from $3, if I add $1 to my revenue, what happens to my attendance? My attendance goes down by 100 people. If I add $2 to my revenue, or sorry, to my ticket price, my attendance goes down by 200. So this starts to give you an idea of where your variables are going to come in. If I add X dollars to my to my ticket price, what happens to my attendance? For every X, for every 1X I go up, I lose 100X in attendance. So for this one, we're going to say, and we want to be specific here, so we're going to let X represent the number of $1 price increases. Okay, you do need to be specific. You have to be specific about whether it's increasing or decreasing, because that defines whether I put a plus or a minus here, and the increments. So for every $1 price increase, I lose 100 customers or 100 ticket sales. So now that we have this, now that we have our equation for revenue in terms of our variable, it's a factored form quadratic equation. We want what ticket price results in the greatest revenue, and you have to be careful here. So let me go ahead and solve the first part of it. So when I've got something in factored form, I am trying to find the greatest, which means a maximum, which means a vertex. So what do I do to find that? Well, the first thing I do is find my zeros. And the way I'm going to do that is I'm going to, in this case, set R equal to 0. So I get 0 equals 3 plus X (800 minus 100X). And that's only possible if 3 plus X equals 0, or if 800 minus 100X equals 0. Now remember, I'm finding the zeros here. So this one gives me X equals -3. Does that make sense? I started with a ticket price of 3. In theory, I could drop the price of my tickets by $3, but then will I have any revenue? No, because then I'll be charging 0 for the tickets, and I may get lots of people coming to the games, but I won't make any money. This other one is 800 becomes 100X. Divide both sides by 100, I end up with X is equal to 8. Now in this case, that's saying that if X is equal to 8, but what is my ticket price if X is equal to 8? That would be 3 plus 8. That would be $11. So if I kick the price up to $11 per ticket, I lose all of my customers and nobody comes to the games. So these are the zeros. These are the two numbers that will result in no revenue at all. Now I want to find my X coordinate of my vertex, which is to add those together. And don't forget, this one's negative. So that's -3 plus 8 divided by 2. That's equal to 5 divided by 2, or 2.5. So again, both of these are fine. And I'm going to hopefully learn my lesson from last time. I'll probably use the 2.5 this time. Now I need to find, well, let's go back. Now we want to take a look. What are we finding here? What ticket price results in the greatest revenue? I have found X of the vertex, and so my ticket price well, what is my ticket price? It's actually 3 plus X, and that is equal to 3 plus 2.5, which is equal to 5.5. So the ticket price is actually going to be $5.5 to maximize revenue. Now let's take a look at part B, which was what is the greatest revenue? Well, that now I want to find the R value of the vertex. And the way that I do that is I'm going to sub the X, or the X value of the vertex, which is equal to, be careful, it's 2.5, not 5.5. So we end up with the R value of the vertex is equal to 3 plus 2.5, 800 minus 100 times 2.5. This one is 5.5. We've calculated that before. And this one is going to be 800 minus 250. And that is equal to 5.5 times, this one is going to be 550. And that is going to work out to be, and I'm not going to trust myself to do that in my head, so I'll just grab a calculator. $5.5 times 550 gives us 3025, 3025. So therefore my max revenue is 3025 at a price of, and what did we want? $5.50. Let me just rewrite that. It's all pretty messy. I apologize for that. $5.50. Okay, I think that might be it. Let's see if there's a fourth example here. So this fourth example, determine the number which exceeds the square of the same number by the greatest possible amount. Now this one is just tough to read, even though it's only one sentence. So we are trying to determine a number. So I'm going to let x be the number. And we want a number which exceeds the square of the same number by the greatest possible amount. So we've got a number which is bigger than its own square. And we're trying to maximize the, so let me put this another way. We are trying to maximize the difference between, we're trying to maximize the difference between the number and its square, and the number is supposed to exceed its square. So we're trying to maximize the difference between x and x squared. So what we actually want is y equals x minus x squared. And we want to maximize y. This is the difference between a number and its square. And we want that to be the maximum possible amount. And to maximize y, that means we want the vertex. We want the x-coordinate of the vertex and the y-coordinate of the vertex. And in this case, we just want to determine the number. So we actually don't want the y-coordinate of the vertex. We just want the x-coordinate of the vertex. So to do that, we're going to have to go to factored form. Y equals x, 1 minus x. Then we're going to set y equal to 0. 0 equals x times 1 minus x. Oh, sorry. And so the way this can occur is if x equals 0, or if 1 minus x equals 0. This one becomes 1 equals x, or x equals 1. Then, step 3, the x-coordinate of the vertex is to take these two zeros, 0 and 1, add them together and divide by 2. So we just end up with a half. And the question doesn't actually want to know what the maximum possible amount is. We just want to know the number. Therefore, the number is 1/2. We found the number. We don't need the y-coordinate of the vertex. Okay, so that is it. There's a bit of a summary here. I'm just going to go through that quickly. So, in quadratic relation word problems, you're going to see some of these, and we've already talked about one of them. Revenue is one of them, and that's how much money is coming in. We also look at cost. That's how much money goes out of the business. So you've got the money that comes into the business, which is considered to be a positive, the money going out, which is a negative, and then profit, which we're quite often interested in. That's revenue minus cost, how much you brought in versus how much went out. Businesses generally don't concern themselves with one or the other of these. They're usually interested in profit, which is the combination of them. And in particular, businesses are interested in what's known as the break-even point. That's because once you get to the break-even point, anything you make above that becomes profit, a positive profit, and that's a good thing. A negative profit is also known as a loss. That's a bad thing. So just keep that in mind when you're looking at the homework for this unit and for other application questions going forward. And there is the assigned work for this lesson.